In this lecture, we are going to look at the use of GRAFCETs in the design of PLC programs. A GRAFCET is a graphical tool that is used for describing a sequencing system. It consists of steps which are associated with actions, transitions, and directed links. We shall use an example GRAFCET to describe these components of a GRAFCET. Steps are the stages that are followed by the sequencing system. In this example, the system has 6 steps that are named step 0, step 1, step 2, through to step 5. The system will start in step 0, then moves to step 1. After that, it goes to step 2, 3, 4, 5, and then back to step 0. Each step may be associated with some actions. In this example, step 1 is associated with output 1. This means that output 1 occurs or is activated during step 1. Similarly, output 2 occurs during step 2, output 3 occurs during step 3, and output 4 occurs during step 4. Steps 0 and 5 do not have any associated actions. Transitions are the conditions that require to be met in order for the system to move from one step to the other. In this example, input 1 needs to occur in order for the system to move from step 0 to step 1. Input 2 will need to occur in order for the system to move from step 1 to step 2, and so on. Directed links are the connections between the steps. Let's consider a system that extends 2 hydraulic cylinders in turns and then retracts them before going into an idle state. Here is the GRAFCET to describe the system. The system starts off in an idle state, which is step 0. When the start button is pressed, the system moves from step 0 to step 1. During step 1, cylinder A is extending. When cylinder A becomes fully extended, the system moves from step 1 to step 2. In step 2, cylinder B is extending. When cylinder B is fully extended, the system moves from step 2 to step 3. In step 3, both the 2 cylinders A and B are retracting. When the 2 cylinders are fully retracted, the system moves from step 3 to 0, which is back into the idle state. As another example, let's look at the GRAFCET for a system that is used to mix 2 chemicals. The system begins off in an idle state, which is step number 0. When the start button is pressed, the system moves from step 0 to step 1. During step 1, valve V1 is opened and the stirrer is turning. Valve V1 allows the first chemical to be added into the mixer. As the chemical is being added into the mixer, the level in the mixer rises. When the level gets to level 2, the system moves from step 1 to step 2. In step 2, valve V2 is opened and the stirrer is turning. Valve V2 allows the second chemical to be added into the mixer. When the level in the mixer gets to level 3, the system moves from step 2 to step number 3. During step number 3, the stirrer is turning and the heater is on. The heater makes the temperature of the mix to rise. When the temperature of the mix gets to the required level, the system moves from step number 3 to step number 4. In step number 4, valve V3 is opened. Valve V3 allows the mix to be offloaded from the mixer. As the mix is being offloaded, the level in the mixer is falling. When the level falls to level 1, the system moves from step number 4 into the idle step number 0. The graph sets that we looked at so far are quite simple, but we may have quite massive graph sets in real life. As an example, the one shown on this slide. You may try in your own time to understand what the graph set implies on the sequencing system that it represents. When graph sets are applied in the design of PLC programs, a step represents a process state. Actions represent the outputs to be turned on in a particular step. Transition points represent the closing or opening of input contacts. In other words, they represent the states of the sensors. Let's look at how we change a graph set into a PLC program. To illustrate this, we shall use a system that puts on a red light and a buzzer when the start button is pressed and a green light when the stop button is pressed. Such a system may be used as a warning device, for example, in the operation of a crane. The graph set for the system is shown. It has 2 steps. In step number 1, the green light is put on. When the start button is pressed, the system moves from step 1 to step 2. In step number 2, the red light and the buzzer are put on. When the stop button is pressed, the system moves from step 2 back into step number 1. We shall begin by developing a PLC program that sequences the 2 steps subject to the state of the start and the stop push buttons. As for the outputs, we shall consider them later on. The steps are represented internally in the PLC using memory bits that are respectively named step 1 and step 2 for the purpose of generating the program. The internal bits are also known as auxiliary relays. The bit step 1 is set when the system is in step 1. The bit step 2 is set when the system is in step 2. Let's look at the ladder rung that determines the state of the memory bit step 1. We get into step 1 either when the PLC is first switched on or when we are in step 2 and the stop button is pressed. The first line represents getting into step 1 when the PLC is first switched on. When a PLC is switched on, it gives out a bit that is only active during the first scan cycle of the PLC. This bit is called the first cycle bit. The first cycle bit normal open contacts are closed during the first cycle, resulting in the output step 1 being energized. The second line on the rung represents getting into step 1 when we are in step 2 and the stop button is pressed. Step 2 normal open contacts represent the state of the memory bit step 2. When we are in step 2, these contacts will be closed. When the stop button is pressed, the path becomes a closed path, resulting in the output step 1 being energized. The third line is for latching the output step 1. This ensures that we remain in step 1 even after the first cycle bit has gone or after the stop button has been released. Let's now go to the rung that is used to determine the state of the memory bit step 2. We get into step 2 when we are in step 1 and the start button is pressed. The line that is shown on the rung is self-explanatory. Once we get into step 2, we will need to kill step 1. To do this, we incorporate the normally closed contacts of step 2 into the latching path for step 1. Once we get into step 2, these normal closed contacts will open, resulting in de-energizing of the output step 1 and therefore killing of step 1. In a similar manner, we will also need to latch and kill step 2. The second line on the rung for step 2 is used to latch and kill step 2. The normally open contacts step 2 are the ones that are used to latch step 2, and the normally closed contacts step 1 are the ones that are used to kill step 2. In other words, step 2 is killed whenever we go into step 1, and step 1 is killed whenever we go into step 2. Thus, we have generated a program that sequences the 2 steps. And finally, we go into the section of the ladder program that is used to turn on and off the lights and the buzzer. The first rung is used to turn on and off the green light. As long as we are in step 1, the green light output is going to be energized. The second rung is used to turn on and off the red light and the buzzer. As long as we are in step 2, the red light and the buzzer outputs are going to be energized. This is the complete program that includes the section that is used to generate the sequence of steps and the section that is used to generate the output actions. It is shown here as a single ladder diagram. Let's have a look on some points of note when writing PLC programs using ladder diagrams. The first point is that outputs may be connected in any order. For instance, in this example, we can begin with the rung for the green light, then go to the rung for the buzzer, then go to the rung for the red light. It will also work if we begin with the rung of any of the other inputs. For example, we can begin with the rung for the buzzer, then go to the red light and green light, or begin with the red light, go to the green light and then buzzer, or any other sequence of these connections. All of them will work as long as the inputs are connected correctly. The sequencing of the switching on of the outputs is dependent on what is connected in the latching and killing path of the respective output relays. The second point is that inputs may be repeated, but outputs should never be repeated. For any given output, you need to connect all the inputs that affect it in such a way as to give the logic function that determines the output. In summary, the steps that are generally followed when developing a PLC ladder program are: 1. Generate the graph set to meet the required sequence of steps. 2. Assign auxiliary relays in the form of internal memory bits to each step. 3. Generate ladder rungs for sequencing the steps. These rungs will determine the states of the internal memory bits. Each rung has a path to enter the step and a path to latch and kill the step. Number 4. Generate ladder rungs that are used to switch the outputs of the system. Here is an exercise for you to try on your own. You are given a graph set that describes extending and retraction of two cylinders. Then you are given some guides for the kinds of sensors that are used. Please attempt and try to generate a ladder program to suit the graph set. Let's now have a look at a couple of examples to illustrate the process of designing PLC-based solutions. In the first example, we are looking at the design of a PLC solution that can be used in a system which, when a start push button is pressed, makes a wagon to move to the right, and when the right hand side has been reached, makes the wagon to move back to the left hand side. The slide shows the system. We can notice that there are sensors on the right hand side and on the left hand side to detect when the wagon reaches each of these sides. Also shown is the graph set to describe the operation of the system. The graph set has 3 steps. Step number 1 is the idle state, which is also the first step that is entered when the PLC is first switched on. The 2 rectangles on step 1 indicate that this is the first step. When the start push button is pressed, the system moves from step 1 to step 2. In step 2, the wagon will be moving to the right. When the right hand side has been reached, the system moves from step 2 to step 3. In step 3, the wagon will be moving to the left. When the left hand side has been reached, the system moves from step 3 to step 1, which is back into the idle state. This is the corresponding ladder program. You can take your time to analyze and understand how it works and links to the system description. This is the block diagram to illustrate the connections that are required between the PLC inputs and the sensors, and between the PLC outputs and the actuators. The sensors that need to be connected to the PLC inputs are the start push button, the left limit sensor, and the right limit sensor. The actuators that need to be connected to the PLC outputs are the mechanism to move the wagon to the right and the mechanism to move the wagon to the left. Let's look at the mechanism that is proposed for the movement of the wagon forth and back. A DC motor mounted on the wagon is used to provide the torque for the movement of the wagon. The wagon itself is arranged to move on a pair of rails. The pair of rails is also used as a power supply point on which the wagon can tap power through the wheels. One of the rails is arranged to be positive and the other one is arranged to be negative. To reverse the wagon, the power polarity of the rails is reversed. This is achieved through use of two conductors named K1 and K2. The conductors are switched on and off by the PLC. The conductor K1 makes the upper rail to be positive, and the conductor K2 makes the upper rail to be negative. The two conductors have interlocking to avoid them being energized at the same time, as this can result in a catastrophic consequence. Let's now look at the circuits that can be used to connect sensors and actuators to the PLC. On the sensors, we have a push to make switch and limit switches. Therefore, we can connect these sensors using the plain switch connection method. For actuators, we are using conductors. We can use a relay or track output card on the PLC. The conductors are then connected in circuits that are turned on or off by relays or tracks on the PLC output card. This correspondingly results in energizing or de-energizing of the conductor contacts and therefore closing or opening of the conductor contacts. The second example is a PLC solution for the operation of a press. We are shown here the graph set for the system as well as support diagrams to help illustrate the operation of the system. The system begins off in an idle state. When material is loaded into position and the start push button is pressed, the stamp is lowered. As the stamp is being lowered, the material is being pressed. When the end of compression is reached, that is, when the stamp gets to the low position, the stamp is raised. When the stamp gets to the high position, the die is lowered. When the die gets to the low position, the pressed material is evacuated. When evacuation is completed, the die is raised in preparation for the next cycle of pressing. When the die gets to the high position, the system returns into the idle state. This is the suggested ladder program for running the press. You can look at it more carefully and analyze it so that you understand how it links to the operation of the press is described. Also suggest suitable circuit diagrams to show how the various sensors and actuators are connected to the PLC. The third example is a PLC solution for the operation of a drilling machine. The material being drilled is held in position by a mechanism driven by two hydraulic cylinders A and B. To hold the material in position, the cylinders have to be extended. To release the material, the cylinders have to be retracted. Before starting the drilling process, the drill has to be lowered. And after finishing the drilling process, the drill has to be raised. There are respective sensors to detect the positions of the drill and the cylinders. Suggest suitable sensors and actuators and then draw circuit diagrams to show how these sensors and actuators can be connected to the PLC. Here is the graph set for the operation of the drilling machine. You can study it further on your own so that you understand how the drilling machine operates. And here is the PLC ladder program for the drilling machine. Also, study it on your own so that you understand how it links to the graph set that has been given. We have an exercise here. You are required to develop the graph set for the operation of an automatic hand dryer. You are given the ladder program, so you can turn this ladder program into a graph set. Also, suggest suitable sensors and actuators and then draw circuit diagrams to show how the actuators and the sensors can be connected to a PLC.